Okay, so as I said at the end of the previous hour, we will be continuing with the dictionary techniques for lossless compression. So let's do that. Dictionary techniques. Oops. Now, the dictionary techniques are many. If you take a look at the books that I have mentioned about, you will see a lot of very nice techniques for compression of lossless data, which has some kind of a structure like the language itself. So if it's text data, if it's a book, for instance, first the letters themselves, sometimes even further than that, the words will start having some kind of a layout, which one comes after which one, and therefore we know that something else will come later. For example, we know that if in English, if you have a letter Q, then after that letter, the next letter must be U. So they don't come isolatedly, they come in pairs. The reason that the techniques, the general class of techniques are proposed as dictionary techniques is because you keep a code book, a kind of a dictionary at one side of the decode of the encoding. So you're encoding your source, and meanwhile, during the encoding, you generate a dictionary and you use it for encoding purposes. And it's an adaptive dictionary in most cases. And the decoder will start decoding, and during decoding it will also generate the same, exactly the same dictionary, and it's going to use that one for the referral. So the dictionary for the encoder and the decoder will be symmetrically constructed, and therefore decoding will be complete. Now the perhaps the most trivial approach to a dictionary based, or a dictionary technique for encoding, is something like this. For example, you look at the dictionary itself, the English dictionary, and you notice that it starts with A. It's the letter A, and it also means one. Okay, there is a something. So A is over there. And then the next word that comes afterwards, and it's encoding for the compression business, its encoding is also A. And the next letter that, the word that you encounter in the dictionary is this thing. I think it's an animal. I don't even know what it is. But the encoding of this could be done as a prefix code of the previous, like this. Did we gain anything? Instead of A, I used one because one is already in the dictionary. We didn't gain anything because the previous word itself is only one letter. So replacing a letter with another letter didn't really much help. And it goes on a little bit like that. For example, we have this word, which can be encoded as this. But then, sorry, it's not. We come up with an abandon, for example, word, and the previous one is aback, and the third in this dictionary is aback, and from that third, from the previous, in other words, it's not the third, but let's use the previous. Let us use 3 letters from the previous, and then continue like this. So we are just looking at the previous word, and we are just copying some of them from the prefix side, from the first side, some letters. Now you see that we are gaining something. The new representation of abandon is 3-anden, and the only way to decode this 3-anden is by knowing or by constructing the dictionary at the decoder side as well. So without decoding this A, you cannot decode aardvark, whatever it is. And without decoding it, you cannot decode one back because it looks at the previous one and takes a look at the, or copies the first letter. So without knowing this, you cannot decode this because it's telling you that look at the previous one's first 3 letters and use it here and then continue. And maybe even more significant than that one is abandoning, which will use 7 of the previous word, which is everything actually, because it's a 7-letter word, abandon. And then ing is using it. You can continue like abandonment, which can copy 7 of the previous, but continue with month instead of abandoning. So this is some sort of a dictionary coding, and as you see, you are gaining something. The representation of the right-hand side, which are the code words, are slightly less than the representation of the word itself. Clearly, we don't use it. I mean, we don't really compress things like this, but it's an approach which shows the idea of the techniques that we are dealing with, which are the dictionary techniques. Now, the next one is a little bit non-trivial as opposed to this one. It is called move to front technique. And I want to do it in an example, over an example, as we always do, because it's the best, most understandable way of doing it. The move to front coding starts with a standard binary tree, which doesn't have any optimization of the binary code word generation according to any specific kind of frequency, but it is a binary tree, therefore it is uniquely decodable and it is unbalanced. So it's like this. At side 1, you have the root corresponding to the it's not the root, but it's the code word corresponding to the most frequent symbol. Let's use only 1 bit for it and use 1 for that, for the first, the most frequent word. And then 2 for the second. I will generate 2 code words which are starting with a 0. So 2 and 3 will start with a 0, and I will construct 2 code words. In order to distinguish between 2 code words, sorry, I will start with not 0, but I will start with 0, 1, because only then I will be able to start other codes with not a 0, 1, but a 0, 0, 1, for example. So with 0, 1, I will construct 2 symbols. The first one will be 0, 1, 0. The other one will be 0, 1, 1. And then, so that makes 2 symbols. Then I will have 4 symbols. 6 and 7. 4 symbols, which will all start with 0, 0, 1 instead of 0, 1, because I want them to be uniquely decodable. So the prefix must be different. I'm constructing prefix codes in the binary tree, and I will have to distinguish between these 4 symbols. How can I do that? The first one is 0, 0, then 0, 1, then 1, 0, then 1, 1. So you get the idea. As you see, the next will be 8 more symbols, like 8, 9, 10, 11. 11, 12, 13, 14. Are we there? No, we need 15. These 8 symbols will all start with the same prefix of not 001, but 0001 to make them distinguished from the previous prefix. I'm not sure whether these are the rice codes or not. I didn't check, but you can use any of those such previously determined uniquely decodable code sets. So this is a set that you can use. So how can I differentiate between these 8 symbols using 3 more bits, starting from 000, going up to 111. So 000, 001, 010, 011, then 100, 101, 110, 111. The next will be, of course, 16 more symbols. But you get the picture. This is an unbalanced and fixed binary tree corresponding to some code words. Now, move to front works as follows. It counts the symbols as they come, as they arrive, and as the symbols arrive, it counts by counting the symbols. The more frequent ones will be moved or pushed to the top, so that they will now be represented with fewer number of bits. For instance, if it's an English text and if the symbols are the words, then probably the most commonly encountered word would be the. After a while, the count of the will push it, move it to the front of this code word list, and it will be represented by one only, using the. Instead of the, you will put a binary code of 1. Other symbols, for example, of, will be moved up to the second level, and every time you see of, you will represent it by 0, 1, 0, only 3 bits long. So that's how you can do it. But how does the decoder know that how does the decoder know how these things are updated? Because this counting is not an initial thing. It is an adaptive process. So we will be adaptively count symbols as they arrive. It's not that we just encode, for instance, the Moby Dick, okay, the book, from the start, from the beginning to the end, and then count how many do's are there, how many offs are there. No, it doesn't work like that. You start from the first word and you start encoding. So it's more towards streaming-like or immediately encoding type of strategy. And I will be showing the, so this is the list that we have. You can forget about it. By moving to the front, we will have shorter bits. Now I will illustrate it with an example of this word, this sentence. It's the boy on my right is the right boy. Now, this is a sentence that is repeating things, but the repetitions are quite arbitrary. For example, the is encountered twice, but the first the is in the beginning, and the second the is not, is like 1, 2, 3, 4, 5, 6, 7th word in the list. So the encoder will work as follows. To the left-hand side, I will do the encoding, and at the right-hand side, we will see that it is actually decodable. The decoder does not need any kind of extra information to be sent. First, the list is empty. Now we are in the encoder. The list is empty. And counter is 0. And then the first symbol arrives. Symbol is the. Okay, it's the first word. So we encode it like this: 0, the. This is just a representation, the curly parentheses, the colon, 2 dots, and things like that. Of course, we don't do it like this in computer implementations. We can use escape codes and things like that, the beginning and ending bits. Just the implementation is really software engineering. But this is the idea that I'm trying to express here. So we have somehow a representation of 2 symbols here. The first one is the count, which is 0, which corresponds to the place, and then the symbol itself, which is the. It must be there because we are going to transmit it. Otherwise, how can the decoder decode this? Decode that one? We will take a look at that in a while. And then the counter is becoming 1. And the second symbol is boy, because it's the boy. And now we are having this word. And it does not exist in the list that we are constructing. The list that we are constructing can be put here. And you can think of it like this. Now, since there is only one word, it is in the list, and the is here. And now, the second symbol is boy. And so we must emit a code like this. 1 boy. And since it occurred later than the new, this is, by the way, the list. The list. And I'm going to illustrate the list. We seem to be disconnected. Are you hearing me now? Can you hear me?
Yes, Professor.
All right, all right. There was a
But
disconnection.
there is a problem in your connection, maybe.
Yes, that is correct. So I will try to continue. Just I'm trying to share. Yes. Now the screen is hopefully back, but my connection is bad. I know. So now we emit the symbol 1 boy, and the new list becomes like this. It's 0 boy and 1 the. In other words, I'm scrolling up a little bit, and I'm going to erase this the from here, and I will insert boy here, and the will be pushed downwards 1 step. Although their counts are the same, why did I do that? Because that's how move to front technique works. For the equals, the last one that arrives will be preferred to be at the top. So the count of the and the count of boy are all the same. And since boy came later than the, boy is at the top, the is pushed down. So if in a next symbol, a new symbol comes as the, I will be just representing it not as emitting a new symbol of the, but I will be emitting 0, 1, 0. Okay, because it's in the list, it would be in the list. But the next word is on, and therefore I have to first, since it's not in the list, I will have to emit it as 2 on, because there are 0 and 1 which are already full, and this is a new symbol. I emit this, and the list becomes 0 on, 1 boy, and 2 the, because they appear all once. The boy on, they appear as one. So we erase them again all over. We say this is on, this is boy, this is the. Let's continue from here. Let's not write all the things on the encoder side, but let's see how they appear inside the dictionary. So let me repeat the sentence. The boy on my right is the right boy. Right? This was our sentence. So the next word will be my. It's not in the list, so it is transmitted as 3 boy. And since it is transmitted, the decoder will know that this is something new. And it will be pushed to the top like my on boy the. Then this will be the new list. The new list in the implicit dictionary. This is a dictionary that I'm not transmitting or anything. This is a dictionary that I'm constructing for my future encoding purposes. And the decoder, meanwhile, it's also constructing the same dictionary, this dictionary, because it first received the, so it put it, the decoder puts it in the at the top, and then comes a new symbol, which is boy. So boy is a new symbol. It is on the top. The is pushed down. Then came on. So on is pushed to the top. The others are pushed down. Then my comes, a new symbol. My is inserted at the top. The others are pushed downwards. And then comes right. So these are all pushed downwards. And right comes here. Right, my, on, boy, the. And then is comes once again. Not once again, but it's a new symbol once again. So every new symbol in this process initially will be inserted from the top, because their counts will be the same. So we again delete these and insert is at the top, right, my, on, boy, the. Until now, we did not really use any of these symbols yet, because we didn't have the opportunity to use these code words instead of the symbols. We are just transmitting new symbols because they are new. There is no way to make a representation of these things. But at this point, when is also is transmitted, the next symbol to be transmitted will become the. Okay, that's a good one. So the transmission until now goes on like this: 0 the, 1 boy, 2 on, 3 my, 4 right, 5 is. So these are the transmission symbols. And when I do this transmission, the dictionary is already full of these 6 symbols in this format. The last one is at the top and the first one is at the bottom, because that's how it works. And then comes the. The is in the dictionary. So we don't transmit it as a separate new symbol by saying 6 the or anything like that. We don't say that. Instead, we transmit the symbol notation of the, which is in the 6th place in the list, and that is represented as the bit stream of 0, 0, 1, 1, 0, because it was there. So this 0, 0, 1, 1, 0 is essentially significantly less than the representation of these symbols before that, because these are not characters that I'm writing, they are bits, whereas these are essentially characters or integers and things like that. And every character, every integer is, for example, 32 bits or 16 bits, whereas these are just 1 bits, as you see. So I used it's just simply 5 bits extra, although it looks longer in my handwriting. So we started achieving the efficiency already. Now, however, the dictionary is also updated. Why? Because the count of the is not 1 anymore. Meanwhile, we are also counting the histogram, the frequencies of these symbols. The frequency of the is 2, as opposed to the frequency of the others, which are all 1s. So it is moved, as the name implies, it is moving to the front now. It is moving into a place corresponding to its frequency. And 2 is the highest frequency anyway. So it's a pity that we are just making push and pops of these stacks or the list. So the now comes to the top again. But at the place where we were transmitting this symbol, it was not at the top, and we didn't transmit as 1 bit, but we transmit like this, because at the position where it is transmitted, this was its representation. So that's what we transmit. Afterwards, the is moved to the front, and the rest is right. They are pushed downwards, right? My on boy. So the is now at the top because its frequency is observed to be 2. Now, what is the next? After the, it's right. Right is in the dictionary, in the current form of the dictionary. This is not a static dictionary. As you see, it's updated all the time while as new elements arrive. At that particular instant, when this right comes, right is in the dictionary and it is here. Right? So we transmit its corresponding code word, which is 011. Okay, 3 bits. Now the count of right becomes 2. We are also keeping account of how many of these things are encountered, the frequencies. So the frequency of right is also 2. So it's the same as the frequency of the, but its frequency reached to this later. So by choice, we put it above the place of the. Above the among the equals, the later one will be at the top. So these are erased or pushed downwards, and we put right to the top. Then the second one is the. These two have frequency the. frequency of 2. The rest is my, on, and boy. They have frequency 1. So this is the current situation or the structure of the dictionary at the point where we start this time emitting the code for this symbol, which is boy. Boy is in our list. It's here. So correspondingly, it is 00110. 00110. We emit this, and the decoder knows that it is boy, because it's also dynamically updating, adaptively updating the dictionary the same way that we are updating the dictionary in our encoder. So this is boy, and now the count of boy is also 2, so it must be pushed to the top. Boy, oh, sorry, boy, right, the is my, on. Now at this point, or at this point, this is the final structure of the table, the dictionary. If you want to transmit more symbols, if it's a new symbol, it will be, now every new symbol will be pushed to this point, if it comes. Why? Because boy, right, and the have counts of those three symbols have the count of 2, and the rest have a count of 1. So a new one will have a count of 1, so it will be at the top of the equals, which is here. So if a new symbol comes after this sentence, if a new word comes in, that new word will be inserted here. Okay, do you see that? And if something new comes, it will be also inserted here. If something among these may arrive later on again, they will be represented using whatever they correspond to in the code book, and their counts will increase, and their places will be elevated. They will move to the front of this dictionary according to their counts. For example, if the count of this is 4, if the count of this is 3, this is 2, this is 2, this is 2, and this 2 is increased one more, then it will be to the top of 3, but after 4, because its count is not 4. 4 will be above it, but among the 3s, the newest one that became 3 will be inserted into that position. So the positioning strategy is fixed. It is determined. It is deterministic, and both the encoder and decoder makes it in a parallel or symmetric way. Therefore, whatever the encoder does, the decoder is capable of decoding. For example, if you are decoding this one, you will decode it as the boy on my right is, because they are already new symbols, so you decode them in this order. But the dictionary will start with is at the top, right, before, after that, my, after that, on, after that, boy, after that, and the last in the list. And then comes this one, which is here, the last. What was it? It was the. So instead of this, the decoder will decode the for this symbol. And its position will also elevate to the top, and the others will be pushed down. And then over there, this would correspond to, after the adjustments, after the updates, in the updated list, this will correspond to right, and it will be updated again. In the new updated scheme, this will correspond to boy, and therefore it will be decoded, and this boy will be elevated to the top of the list, and the dictionary will be updated. Now, as you see, there is something very strange that has happened, but we know why it worked that way. It's this. This code word is identical to this code word, But when this code word is emitted or decoded, it was corresponding to the 00110 corresponds to the, and later on, once again, 00110 came, which is exactly the same as this one, but this time it corresponds to boy, not the. Interesting, isn't it? I mean, we are using the same code words for different purposes because this dictionary is being updated all the time. It's a dynamic list. This is the move to front technique. And as you see, since there are only a finite number of words that is usually used for constructing a text, I don't know, maybe 200 words only. So those 200 words will be rendered in a 200 element dictionary, and the more frequent ones will be moving, they will be climbing upwards in the list, and they will be represented with fewer bits, and the less frequently encountered ones will be left out at the bottom. So anytime you encounter those rarely encountered words, uh, you will use more bits, but if you use a more frequently encountered word, you will use fewer bits. And of course, the counts will be incremented or they will be updated. So this is a dynamic list in this move to front technique. And its implementation is maybe slightly more difficult than what we have for static code word generating algorithms such as half-moon coding or Shannon funnel coding. But this is what move to front technique is. And it is technically manageable, it's doable, and it's a good technique. People just use it for several purposes. Now, before stopping for
Can I
today,
ask a question?
oh yes, please.
Uh, can you go to the last page?
This one?
Yes. Why we used here zero the and we use 011.
Yes, here. Here, you mean?
Not here. Yes, here.
Yeah, under this. 011 was the representation of right. In that position, in the position where after the comes, so after encoding the here, now we want to encode right, and right was already in the dictionary, and its representation, as far as I remember, was 011.
Okay.
That's why I put 011 for representing right. And then, of course, the position, the place of right increased to some other place. It became the top, which is one represented only by one. But while encoding this right, it was not one. It was 011. So that's why I use 011 and then update it.
Okay. Thank you.
We do the update after first using the dictionary because if we first update and then use, the decoder will not know that. The decoder is using only the available. So using the available, we first use it for encoding so that the decoder will decode. And then both the encoder and decoder simultaneously updates the dictionary. And that's how it works. Okay. Now, the last thing before giving a break is the easy way of doing the so-called Lampel-Ziv encoding. Lampel-Ziv coders, let's say, sometimes also abbreviated as LZ coders. And these are very popular. In fact, nowadays the computers just use these techniques. There are three famous variants of Lampel-Ziv coders. The first variant is Lampel-Ziv 77, which I will show now. Then is LZ 78, which I will show next week. And then the next is LZW, which I think I'm not going to show. But the way it works is also quite commonly known. So it may be, I don't know, maybe it may be a question for asking for application of an LZW for a sequence. I may ask you, for example, apply uh, these symbols and this input source to LZ77, 78, and LZW, and write down the answers to the paper, and that will be a question of the first midterm for the in the form of take home. But the idea, after you see LZ78, you will understand what LZW looks like. LZW is had been more popular among these, and LZ78 was also somewhat popular. So some variants of these two had been used in compression algorithms in computers in terms of zip and things like that. Zip, I think, is using LZW, which is a variant of LZ78. LZW, this W is, by the way, Welch. So it is Lampel-Ziv Welch coding. These are just collaborating scientists. From these words, I think they may be Jewish. Ziv particularly sounds like a Jewish name. Yeah, whatever. These scientists, I didn't check the papers. I didn't see the papers either. I just know the algorithms from their narratives from books. Um, but as far as I know, the LZ77 is very much time and memory consuming. Is more time and memory consuming as opposed to the other variants, which are constructing dictionaries to uh, fasten up to make it faster and with less memory searches and things like that. So these two are faster variants of LZ77. By the way, this 77 is corresponding to the date that the paper was published. So it was 1977 that this method was invented. And 1 year later, LZ78 was invented, which is a speed up improvement of LZ77. But that speed up improvement comes with a compromise of slightly less efficiency because it's using dictionaries. So dictionary is not containing the history itself, the whole history, because looking at the whole history takes a lot of time and it's very memory consuming. So instead of that, a smaller dictionary is constructed in LZ78. We will see that. But the overall efficiency deteriorates a little bit. So now, after some time, once the computers became more and more powerful, for example, today's computers, the compression utilities prefer to use LZ77 actually. We go back in time and use the earlier variant, which is slightly more efficient in terms of compression efficiency. And since the computers are powerful and the memory of the computers are increasing, ever increasing, it is now feasible to use, again, LZ77. So what is that LZ77? It's essentially something like this. Suppose that you, again, let's see it over an example. Suppose that our symbols are, or our source is consisting of letters, and it's like this: A, B, C, B, B, A, B, C, like this. The encoding of this is as follows. We start from here, from the left, and we proceed to the right, okay, this way, from left to right. And let's say that we are here. For the first symbol, there's nothing to do. So what we say is, it may sound awkward and it may look like expanding the data, but it is indeed expanding the data if this much short sequence is being compressed. The longer the sequence becomes, the more efficient it will get. it is telling, it is consisting of first two symbols. The first symbol means go back how many symbols in the source. So go back 0 symbols because it's the first symbol. And then the second item to be encoded is copy how many from that go back position. We copy nothing, we copy 0 symbols. And then after whatever went back and copied, the next symbol that arrives is A because it's the first A. And then we look at the second A, which has one A before that. So what we can do is we search for that A already, which is saying something like this. After this first A, go back one item and copy one more item, which was A. So the first, this one made an A, and this place made another A by going back by one and copying it. Now we have A, and the one comes after that is the new symbol, which is B. So now the decoder, if the decoder receives these two, it will be able to decode it as A. Now go back and copy again A, and the new symbol is B. So AAB is already encoded and decoded. So we are now here, which is C. Do we have any repetition before that? No, nothing. So we can't copy or anything. We can't uh, paste anything. So we go 0 items and copy 0 things, and the next is C. So now here, AAB was already there. Now it's C. The decoder is capable of decoding this much. So now let me erase this part. Now I arrive here, and I notice that it's B. I can go even one further. I can take a look at the new symbol of BB, if it is in the past or not. But BB is not in the past. So every time I arrive, I'm making a search to the backwards side, and I can see that B is in the past. How much past was the location? You have to go two symbols from here and arrive from here, go back two symbols and arrive at this B, and copy one of these B's because there was one B. If you copy two things, it will copy BC, which would be incorrect because it is BB that we are trying to encode. And now the next symbol is another B. So all of these things can be now decoded as AABC, which was already decoded. Now go back two items and copy this again as B, copy one again, and then the new symbol is another B. So now we are saying AABCBV. We have decoded this much. Now I will erase the left-hand side. So I'm oscillating from right to left and left to right. So now I'm at this encoding position of A. And this A actually appears in the past. It appears here or here. And when I take a look at AB, in fact, AB altogether also appears here in the past. I could also look at ABC, all of it. And even that one exists in the list. So I could say like, go back 1, 2, 3, 4, 5. Go back by 5 and copy these all three items A, B, C, and it will be here. But then, because of the structure of the LAMP zip coding, after going back and copying, I must have some new item here, and I don't have it because this is my message, this much. So I have nothing here. So I have to use this C as the last message item to be encoded. So I have to do it like go back by 5. Instead of 3, just copy 2. Just copy A and B, and after that comes C. And this whole thing corresponds to A, B, C, B, B, A, B, C. So how did it work? It works by searching the past. You are going to the past. If the new coming symbols appear in the past, just find them one by one. For example, you first search for A because we are at the symbol of A. Is A in the past? Yes. Now add one more, AB. Is AB in the past? Yes, it is also in the past. If longer things are also in the past, you have to continue searching for all of these things as well. But since, as you see, it requires iterative ways of making searches, longer and longer searches, as the sequence increases, the search window size will extend to technically infinity because many new symbols may arrive. Think of a very thick book like The Miserables, right? It's a huge book, and looking at the past would take a lot of time. That's why it wasn't preferred. This is a method which is technically very efficient for finding the repetitions, because history is made of repetitions. That is the whole idea. So anytime I see something, I will probably find the same pattern in the past. So let me search for it. And if it is in the past, let me not use this new pattern for representation again. Let me just indicate it by saying that go back this much and copy this much. These two numerical items will be incorporated. Go back and copy, go back and copy. Those copy pasting lengths will of course grow longer and longer, and the longer they grow, the more efficient this LZ77 becomes. And as I said, nowadays computers are literally using this. 7-zip or something like this, as far as I know, is using LZ77. But I'm not sure about that. For the curious, I may recommend that you may research what techniques the currently popular compression tools use, and they will indicate what technique they are using. It's usually a variant of these dictionary techniques, probably LZW or LZ77 or something like that. Okay, so this is how LZ77 works. LZ78 is an attempt to avoid indefinite searches to the backside by constructing a dictionary. So it's more like move to front kind of coding. We will see that, but we don't have the time to discuss about these things for the time being. So it's a good idea to stop the lecture at this point, and we will continue with LZ78 next week at 9:30. So I'm stopping at this point, but before stopping, maybe I can ask you if you have any questions or not. They are very understandable. I may recommend that you can just exercise a little bit. The books, if you can find copies, they have examples. Just investigate the examples so that whenever you encounter such a question for implementing, human-wise implementing these methods, you won't suffer a lot, but they are easy anyway. So as far as I see, there are no questions, which means I will first stop recording and then stop the lecture and the meeting.